This is geometry lesson 3.6, parallel lines. The big idea says when a line intersects two or more parallel lines, the angles that are formed have equal measures. So hopefully this seems somewhat of a review from some things you've studied before. But we're going to talk about parallel lines when they are cut by a transversal, which is just a line that intersects two other lines. So if you look at the picture, you've got two lines and they're both being intersected by this third line. So this line intersects two other lines, it cuts those lines. You'll hear that term a lot. That's called a transversal. These two lines are only intersecting one other line, so we would not call those a transversal, but any line that intersects two other lines we're going to call a transversal. There's 8 angles that are formed. All right, and some special things happen when we have parallel lines. Now the corresponding angles are the angles in similar location with respect to the transversal. So we've got this coming through and we get these two different sets of 4 angles. The corresponding angles are the ones in the same spots. So 1 corresponds with 5. Okay, it's in the top left position of this group. It's in the top left position of this group. So corresponding angles, that would be angle 1 and angle 5. We also have 3 and 7. We have 2 and 6. And in the bottom left of each one of these groups of 4, we have angle 4 and angle 8. All right, those are corresponding angles. Now, in a picture like the one here where we don't have parallel lines, there's really nothing special about those. But as we slide down and take a look, the corresponding angles postulate is going to give us some special situations that we're going to study specifically, and you've most likely seen this before. So suppose 2 coplanar lines are cut by a transversal. It's just setting this up. A, if 2 corresponding angles have the same measure. So if you look over at this picture, you've got these groups of 4 angles, the corresponding ones right here in the top right position, angles 1 and 2. You see that marking. We've talked about that means that those angles are equal to each other. So if you see corresponding angles in the same position that have the same measure, then you automatically know that these 2 lines are parallel. Now, one thing you want to look for are these extra arrows that you see on these lines. Okay, that's going to mean parallel. But according to this postulate, even if these symbols weren't here to tell you those lines were parallel, if you have 2 lines cut by a transversal and you have equal angles, you automatically know that those are parallel. That's what letter A says. And letter B is kind of going the opposite direction. If you know that these lines are parallel and you don't see that these angles are equal, you're allowed to assume that they are. So corresponding angles have the same measure. So it goes both ways. If you see 2 lines cut by a transversal and you see equal angles, you know they're parallel, and vice versa. If you see 2 lines and you know they're parallel, you automatically know these angles are equal to each other, even if it doesn't state that in the picture. Okay, so with that, we go down to example 1. When we have these very specific types of pictures, so again, notice the arrows. That's telling you that these are parallel. And because we have parallel lines, part B of the postulate holds true. We can go ahead and fill in all of these angles, and I'll show you how. Specifically, the corresponding angles have to be equal. So when you see 85 degrees right here, I know angle 8 is also 85 degrees because out of this group of 4, bottom left, out of this group of 4, bottom left. Those are corresponding angles. If these are parallel and this is cut by a transversal, we know that they're equal. Now, if you see the question is asking you for angle 7. So based on our postulate here, we only know about these 2 angles, but based on everything else we know with vertical angles and supplementary angles, we can fill in this entire picture. So we'll get to 7 in a second. But first of all, 85 degrees right here is vertical to this angle 2 up here. These are vertical angles. Okay, so those have to be equal. So that's 85 degrees. And if this is 85 because of corresponding angles, this is 85 because of vertical, or once you knew angle 2 is 85, 6 is 85 based on corresponding angles. So eventually we are going to be going back into proofs like we studied in the last chapter. And I know that these are 85 degrees either by the vertical angles theorem, or I know that there are corresponding angles, and that's the corresponding angles postulate. So we'll have to go back and prove this stuff, backing it up with our theorems and our postulates. Now, once we've got these 85 degrees all spread out, we can look at linear pairs and supplementary angles. Okay, so these two angles form a straight line at the bottom. These two angles form a straight line here on the other side. And 1 and 3 are vertical, so they're going to be equal to each other. And they're also going to correspond to 5 and 7. So those are going to be equal to each other. So you can see these are 85, and these are going to be supplementary to 85, and they're all going to be the same. And that's going to be true every time we do one of these pictures. You're just going to have two angles spread out throughout the whole thing. So I'm going to take 180, and I'm going to minus 85, and that means these other angles are 95 degrees. So angle 1 is 95 degrees because these are a linear pair. Angle 3 is 95 degrees because it's vertical to this, or because it's a linear pair with either one of these angles. And now 5 and 7 are also 95 degrees. They are corresponding angles to 1 and 3. They're also supplementary to 6 and 8, and they're vertical to each other. So there's lots of different ways to prove this. But as you can see in this picture, when you have two parallel lines cut by a transversal, if you have one angle, you can find all the angles. It's just going to be two numbers spread throughout the whole picture. So let's practice one more. Okay, we're going to find all the measures of the corresponding angles here. So we're given one, and we're going to go find all the others. So if this is 55 degrees, I know the vertical angle is also 55 degrees. And if you notice in the picture, it does not tell you that we have parallel lines here. So that's a little bit of an oversight on my part there. It would have to be given to you that these are parallel, otherwise you can't actually fill these angles in. So I should have stated that line L and K are parallel. If that's not given to you, you can't start filling in these angles, or it has to be given to you in the picture with those symbols like we talked about, those arrows there. Because if those lines aren't parallel, these angles aren't equal. Okay, but now let's assume these are parallel and fill these in. So we've got 55 and angle 7 is vertical to it. The corresponding angles up here are 1 and 3. They're in the same position as the 55s. So I know those are 55s. And then the angle right next to it is going to be supplementary. So 180 minus 55 is 125. So whichever one you want to kind of start with, these are going to be supplementary. So this is 125. These are vertical. So this is 125. These are corresponding. And so they're 125. But again, these are supplementary. These are supplementary. These are vertical. These are corresponding. Lots of different ways to fill this in. Okay, so that's your basic way to fill in one of these pictures. Now let's talk about the slopes of parallel lines. We've talked about this earlier in the book. We know that the slopes of parallel lines are going to be equal to each other. So the parallel lines and slopes theorem says two non-vertical lines are parallel if and only if, there's your biconditional, they have the same slope. So if two lines have the same slope, they're parallel. If two lines are parallel, they have the same slope. It's a biconditional. You got to be able to read it both ways. Now notice it says non-vertical. A vertical line that goes straight up and down, it doesn't have a slope. It's undefined. Okay, remember that your slope formula, subtract your y's on top. So -3 minus 2 right here, y values. Subtract your x's. When you have a vertical line, you end up with a 0 on the bottom. And so when you can't divide by 0. So it's undefined. And I just like to think about it like this. When you look at the picture, a slope is telling you how fast this is rising or falling. And if it's straight up and down, there's no way to measure that and say how fast is this going up or down. It's straight up and down. You can't measure it. And if we take a look at horizontal lines, they do have a slope of 0. It's not going up. It's not going down. That can be measured. It's 0. Again, if you take a look at those 2 points, subtract your y's, -1, -1 on the top, subtract your x's, 1 minus 4 on the bottom. You're going to get 0 on the top because the y value is not changing, and 0 divided by anything is going to just be 0. So this is the only situation where we have that undefined slope. We can still have parallel lines if they both have that undefined slope. But other than that situation, our parallel lines and slopes theorem says if the slopes are the same, the lines are parallel, and then vice versa. If the lines are parallel, the slopes are the same. It works both ways. Again, that's the biconditional. All right, so example number 2, we're going to find the slope of this. You've done this before. Just quick review of the algebra here. We want to get this into y equals mx plus b form if we want to have the slope. So we got to get the y by itself, minus your 2x. Make sure that minus comes down with the 5. Can't combine, keep these separate. Divide by -5 all the way across. Y equals, 2 negatives cancel. 2/5 x, 2 negatives cancel. Plus 5, you've got your slope and your intercept, but the most important part here is the slope as we relate this to parallel lines. So if you're given the equation of 2 different lines, if you can get them both into this form and see the slopes, you can tell me if they are parallel or not. They're going to have the same slope. And the last one, this makes sense. The last theorem for today, the transitivity of parallelism theorem. That's a hard one to say. Transitivity of parallelism theorem. So this is your transitive property. Oops. And if you remember what that says, A equals B and B equals C, then we know that A equals C. So B is equal to both A and C, therefore we know A and C are equal. That's the transitive property, so now we're relating that to parallel lines. If some line, line L, is parallel to some other line, line M, and line M is parallel to another line, line N, then we automatically know that the first one is also parallel to the last one. So 2 lines are parallel. This one's parallel to another one. That means the first and the third are also parallel. That's what it says here, in other words. In other words, if 2 lines are parallel to a third line, then they are parallel to each other. So taking the transitive property, applying it to parallel lines.